What is a heat pump and how does it work? My name's Alan Hart, and in today's video we've got Peter Armstrong from Mixergy, and Peter's the CEO of Mixergy, and he's going to tell us how a heat pump works. He's going to do a detailed slideshow starting from the basics and then all the way up to fully how it works, and then also he's going to show us some demonstrations of some products, some Valiant heat pumps, some cylinders, and explain how it works. Show it frosting up as well with the ice on it. Please bear with us a little bit with this video because I plan to go down to Mixergy and do this video with them, but because of COVID and we've restricted travel, etc., we've had to do it remotely, so it's a little bit more tricky to do a detailed video. So as I said, please bear with us with that. Without further ado, I'll pass you over to this slideshow, and then, as I say, at the end or near the end, there'll be more detailed showing you the products as well. So yeah, let's have a look at this.
So what is a heat pump? I think to some people it's a bit like a magic box in that you can somehow get 3 or more units of thermal energy into the home for 1 unit of electricity. And if this was true, it would violate the first law of thermodynamics in that you can't create or destroy energy. You can't magic heat out of thin air. So what's going on? And another thing that seems incredible is that we can go from a low temperature outside, say 5 to 10 degrees, and deliver heat to the home at temperatures in excess of 50 degrees with a modern high temperature heat pump. And that seems to violate the second law of thermodynamics. And what do I mean by the second law of thermodynamics? Well, if you think of a cup of hot tea in a room, intuitively we know that heat escapes from the cup to the room and it cools down until it eventually reaches the same temperature of the surroundings. That's common sense. And if we think about it really carefully, we can imagine little molecules, water molecules that comprise of tea, shuttling around and exchanging their momentum, diffusing their momentum to sparse, lower energy air molecules in the cool room. And you've also got heat escaping out of the top of the cup as water evaporates from the surface of the tea. But what if heat were to flow back into the cup of tea? Is that something that we could conceive of? Because does this process work in reverse? Can you get collisions from air molecules that are cooler actually randomly hitting molecules within the water of the tea to make them heat up? Well, the second law of thermodynamics says no, this cannot happen. And this is something that it's quite a deep principle within thermodynamics, and it has quite wide implications about the tendency of systems to go from an ordered to a disordered state. But for our purposes, we just need to know that spontaneously we cannot expect something which is at a low temperature to spontaneously concentrate its energy into a higher temperature. So what's going on with the heat pump? And it seems to be breaking both the first law and second law of thermodynamics. Well, I think it helps if we firstly disabuse ourselves of the idea that we're breaking laws of thermodynamics. Don't worry, as in season 6, episode 21 of The Simpsons, we obey the law of thermodynamics in this house. And if you don't know the reference, Lisa Simpson tried to make a perpetual motion machine for a school science project, and this wound up her dad, Homer Simpson, as you can see. So back to the magic box analogy, I think a better analogy is a conveyor belt. So a heat pump is a bit like a conveyor belt for heat, really. The power going into the electric compressor motor within a heat pump is a bit like the motor driving the belt which is carrying thermal energy from the outdoors into your home. So we're not breaking the first law of thermodynamics. We're simply taking heat that's already from outside and putting it into your house. But then what about the second law of thermodynamics? Well, to address this, let's conduct another thought experiment. If you take a cylinder with a piston of air and let's say you leave it outside on a cold day at 0 degrees outside, then the system, this system, which is a piston, a plunger, a can of air, it will also get to a temperature of 0 degrees. Now, if you were to suddenly squeeze the piston, the air inside would heat up. And if you were to squeeze really hard, you get the air temperature to go up to 50 degrees, let's say. You'll have had this experience if you've been pumping a bicycle tire and the little tube that goes into the inner tube whilst you're pumping. It's the same principle. So now you've got a piston of compressed hot gas. And let's imagine you took this into a house and you just left it in the house. So the piston's inside the home and it's cooling down to its surroundings. So as it cools down, let's imagine this piston's in the living room. It cools down from 50 degrees all the way down to 24 degrees, let's say. And at this point, you're not transferring any more heat. Because as we learned earlier from the second law of thermodynamics, there's no way for heat to spontaneously concentrate and elevate its temperature. So we're at 24 degrees. So we take this cylinder back outside. It's still compressed, but it's cooler. And we just let go. We let go of the piston so that it can expand again to the same pressure as the surrounding atmosphere. Now, because we've taken heat out of the piston when it was sat cooling down in the house, it's actually now going to cool way below 0. Its starting temperature, if you remember, was 0 degrees. And we've taken energy out of this piston when it's at the same pressure as the surrounding atmosphere. So to compensate, the temperature has to go down. And so we're in an environment that's at 0 degrees, and we can get heat now transferring from the surrounding environment into the piston, and eventually the piston will warm up again from -5 back to 0 degrees, back to where we were at the very start. Now you could imagine running this over and over and over again in a cycle. So you take your piston at 0 degrees, you compress it again, it heats up, you carry it to the house, let it cool down, take it back outside, release it, -5, leave it outside to warm back up to 0, and so on and so on. And so this is essentially what a heat pump is doing in a physical sense, except we're just not carrying pistons of air in and out of your house. So one of the really important equations for a heat pump defines the coefficient of performance. This is defined as the heat out versus the energy in. So the amount of heat that you're getting in for the amount of energy that you're having to invest squeezing and releasing this piston. The other very important equation is the Carnot efficiency for a heat pump, which tells you the maximum theoretical coefficient of performance that you could possibly obtain. And that depends on TH, which is the heat that you're trying to get, the temperature of the heat that you're trying to dispatch at. So let's say you want 50-degree system loop temperature to warm some radiators and a hot water cylinder. And TL is the temperature of the outdoors. So that might be 2-3 degrees on a cold winter's day. These temperatures determine the maximum coefficient of performance by this ratio. And one thing to note is that these temperatures are expressed in Kelvin for this to work, not degrees Celsius. So if you want to work it out for degrees Celsius, you have to add 273 before putting it into this formula for each value. So theoretically, using this formula that we saw on the right-hand side of the previous slide, we can plot these lines which show the maximum theoretical coefficient of performance for different temperatures. So if we were trying to dispatch heat at 40 degrees and we had an outdoor temperature of, let's say, 10 degrees, theoretically we could get a coefficient of performance as high as 10. So in other words, for every unit of electricity that goes into our system, we can shift 10 units of heat with our conveyor belt. And if the temperature outdoors goes down, the coefficient of performance theoretically drops, and it also rises the higher the ambient conditions are. The closer the ambient temperature is to the temperature you want to dispatch heat to, the higher your coefficient of performance. In reality, however, the coefficient of performance of a heat pump is quite a bit lower than the theoretical prediction. So, for instance, this graph shows the coefficient of performance for a heat pump. I think it's a Mitsubishi unit, where we're plotting the flow temperature on the bottom axis. So we can, if we're going up to 50, 60 degree flow temperature, the coefficient of performance for outside, where the outside air is 2 or 7 degrees, it's going to be dropping below 2.5 and approaching 1.5. So that's the reality. Still good. I mean, it's still much better than just getting 1 for 1. You're almost doubling your heat or the amount of electric power that you're using in reasonably cool conditions. So going back to what we were talking about earlier about a big piston of compressed air, why don't we just pump cold air into our house like an air compressor and then release it back outside? And the principle would be the same, and it might be a quite simple arrangement. Well, the reason for that is air is a very diffuse medium for storing heat, and you need a huge amount of air. And to compress that amount, carry it into the house, would be very complicated, noisy, and it would actually be very inefficient because it'd be quite a type of equipment you have to pump all that air. So instead, what we have is a heat pump, and rather than pumping air directly into a house and compressing it, what we use is an intermediary fluid called a refrigerant that does the heat exchange process for us and is able to carry heat with a much greater density, if you will, in comparison to air. So this diagram shows what the layouts, and if you look at number 1 over the top left, you've got the source. You get air source or ground source heat pumps. It's all the same principle, and whatever the source is, whether it's air or whether it's water glycol flowing through the ground, it exchanges its heat, the air by a blower or the pumped water from underground, with an evaporator, which is a heat exchanger to the refrigerant. It boils the liquid in this evaporator as it's going into a heat pump compressor, which is this circular item here. And the compressor takes gaseous refrigerant and raises its pressure. And as it does so, it raises its temperature, as we saw earlier with the piston of air. The temperature raised up to, say, 50 degrees, we transfer heat into this second loop. This system loop could be similar to what you'd experience in a normal gas system boiler. It's just a lower temperature typically. Once the condenser is settled and at pressure, it then enters an expansion valve, which allows the refrigerant to escape and depressurize into the evaporator. As it depressurizes, its temperature plummets in the same way that the temperature of the piston that we had in our thought experiment dropped -5 degrees when we let go. The expansion valve, letting the high pressure condensate out into the evaporator, also causes the refrigerant to cool down significantly. And because it's so cold, heat flows from the source, be it air or the ground, back into the refrigerant, warming it up before it goes into the compressor. So that's the principle, and the system is taking electric power from the grid to drive the motor in the pump in this compressor arrangement. So that's it. No mystery, no magic box. It looks basically like a domestic fridge. It's exactly the same principle, and indeed air conditioning systems are also the same principle, but they operate in reverse. So today we're going to be hooking up a Mixergy heat pump ready cylinder to a Valiant aerotherm system, and this is the technical layout of the heat pump, the air source heat pump that the Valiant unit that's inside the Valiant unit. And we can see here we've got a fan which blows air across a radiator. This is the evaporator, and the refrigerant flows through this radiator as it's being warmed by the surrounding air, and then it goes into the compressor. Now, what's interesting here is uh, we've got a reversing valve, which I'll come back to in a moment. But if we ignore this for a moment, the refrigerant under normal circumstances will just go through the compressor into this condenser, which is a heat exchanger, typically coupled to a plate heat exchanger, which gets hot, and we flow water through this to the system loop, which can heat the cylinder, the various zones throughout the house, and the radiators or the underfloor heating. And the refrigerant goes into an expansion valve, and when this expansion valve releases and the refrigerant comes out cooled into the expansion radiator here and round again. So this reversing valve arrangement, this will allow the system to be reversed for defrost. So when the outdoor temperature is really low and if the humidity is high, you get ice building up on this surface. And so if we reverse this valve, we can use the pump, the compressor pump motor to drive the refrigerant into this radiator and heat it up. And the expansion valve is actually an electronic unit which closes off at this point, so that the flow can't keep going round in the other direction. It just only allows you to compress some of the refrigerant into this radiator, and then it heats up and defrosts. And once it's defrosted, it will start running in heat pump mode again. So today we're going to be talking about the performance of this heat pump unit system, and when it's heating a Mixergy heat pump ready cylinder. This is really a proxy for any cylinder, but there are a number of benefits that the Mixergy system has. One is that we're able to utilize the capacity of the cylinder much more effectively with our heat transfer module that sits on the outside. That means that you can get up to a third more hot water from the same cylinder size. You can install a smaller cylinder or have a slimline version, quite a lot of flexibility. Because they're heat pump ready, of course, you can install a gas boiler today, or a tank that's just using direct electric, and retrofit with a heat pump in the future with our heat transfer module. Also, other features to this are that you can see how much hot water is in the tank at all times, and the system's connected to the internet, so it can make use of smart tariffs so that the tank can find the best deal, the cheapest time to use electricity during the day. For more information about this, see Alan's videos, other videos in links below. And we'll now go outside and have a look at this Valiant heat pump system and see how it performs when heating the Mixergy heat pump ready tank.
So behind me we have a Valiant 8 kilowatt air source heat pump. It's a monoblock system that's going to be heating the Mixergy heat pump ready cylinder inside our test lab. It's quite cold tonight, -1, about 90-something% relative humidity, and so we're going to open this up a bit later and see how it performs as it heats up the system inside. So we'll get back to that later. So we've taken the lid off this heat pump and you can see the radiator, the fan, this compartment here within which we have the compressor, the condenser, the plate heat exchanger and the expansion valve through which the refrigerant flows. We've also got the electronics which modulates the speed of the compressor motor. So the refrigerant comes out of the expansion valve over here into this radiator, and as it depressurizes it goes from a liquid into a gas state, gets very cold, and it's this drop in temperature that allows us to transfer heat from the air that's flowing through the fan through the radiator. It gets much colder than the surrounding air, allowing us to get heat back into the refrigerant. Once the refrigerant has been warmed by the outdoor air, it goes back into the compressor, which raises the pressure and the temperature into a condensate, basically. So it's turning from gas to liquid. That raises the temperature of the plate heat exchanger, and we can then pump the water through the system loop back into the building. So the reason we've got the lid off this evening is it's about -1, 98% humidity. So we're interested to see how this performs whilst it's heating the Mixergy heat pump ready cylinder. So we'll come back in a while and have a look at the system as it heats up.
So here we have the Valiant control panel, which is connected to the heat pump outside, and we've also moved the Mixergy tank gauge to the left to show how much hot water is inside the cylinder as the system heats up. At the moment nothing has happened, we've just started the system up. We've had about 0.5 kilowatt hours of energy consumed by the heat pump through some tests that we've been undertaking earlier. And now I'm going to just call for heat by just simply pushing the up arrows. You can select however much heat you want, but we're going to go for a full cylinder. And it's now calling the Valiant heat pump from the Mixergy heat pump ready cylinder. And as it does so, we should get heat flowing through the system loop into the plate heat exchanger, and we'll come back and see how much energy has been consumed through the Valiant heat pump control interface here. So here we can see inside the heat pump, and as we can see we've got air being blown over the radiator by the fan on the right, and the radiator is already beginning to ice up. It's been 20 minutes since Ren called for heat via the Mixergy heat pump ready cylinder. So we're going to keep an eye on this as it gets the cylinder up to its maximum temperature, and we'll see how much energy the heat pump has had to use in order to heat the cylinder.
The heat pump cylinder has finished its heating, as you can see from the gauge that is showing 100% safe charge. So based on the reading of the heat panel, it's giving a COP about 1.2. But bear in mind, it's -1 degree outside and it's humid, and you have frost building up around the radiators. So throughout the seasons, with better weather condition, we'll be expecting around 2 to 3 COP.
Thank you very much for that, Pete. Hope this video has been of some use to you. I'm going to try and do some more videos on this, but I will go down and we'll take stuff apart, and I'll try and do them a little bit more like what I do with my normal videos. Sorry about the sound quality on this a little bit. As I say, because of COVID, this has been a little bit more of a tricky video to do. Obviously, when I'm doing the video myself, I can go into a customer's house, I can video it, and I can put some volume, I can voice over some of it when I need to. But hopefully you have found it of some use. If you do have any questions, please ask them below. That's really, really important, because if you ask them below, when I go down to see these heat pumps and we strip them down and stuff, I'll have lots of questions that I can answer in the videos. So yeah, thanks for watching.